Hi, Neil. Pleasure.
Good morning, everyone. Welcome to our first ever Microscopy Live. I'm Jen, that's me in the pink mask. This is Lorelei in the other mask. So this is going to be basically an hour of interactive scanning electron microscope time. So for context, we're both geologists, so today we're looking at a rock. It is not a rock I've ever seen before, and it's not one that Lorelei knows very well either, so we're going to do a pretty accurate rendition of what it's like when you get a weird sample and trying to work out what happened to this rock hundreds and thousands and million years ago to explain why it is the way it is today. So generals, if you have any questions or you would like to interact with us in a way, you can either use the raise hand function or plonk it in the chat and we'll get to you. Through the magic of Zoom, when we share the screen that we have our software on, we'll actually be able to give somebody control, so you can click on things on the screen and control the data that we collect. And what we're going to do is we're going to use all the data we collect today to make a little handout, which we'll send around to you along with the recording of today's session. So you can see what you've done, because we will be doing some actual science, which for us is very exciting. Oh, sorry. So we're just making sure we've got everything muted. And we're currently on about 4 different computers, trying to get everything to work.
It might be that one. That one.
Yeah. With me. Yeah. Everything is muted at our end. Yeah, so if you do have any questions or anything, just drop us a message in the chat or raise your hand and we will get to you. We'll answer as best we can. So Lorelei is going to give us a quick introduction to our microscope today, and then we'll start doing some science, I guess.
Today we're going to be working on our Gel 7001, which is our field emission microscope. So it's a lot more fancy and a lot more stable, and a lot more high powered than some other electron microscopes. So yeah, currently we're just on, sorry, my hands are here, on this screen, which is the live image. So currently this is going to be very shaky, I do apologize. This is currently what is live on the microscope. We got that, and then if I move this slightly, this is the microscope. They're quite big. This is quite.
Yeah. So this is about my height in the lab. So what we have at the top of the microscope, in the top of that beige tube, that is where basically all the electrons come down from. So what we're doing is using about, I think we're on 15,000 volts today. And we're basically electrocuting a rock. What that does is that electron beam comes down, it interacts with the sample at a really good vacuum. So we've got no oxygen in there rattling around either. And what it will do is it will excite the atoms at the top of the sample surface. They will then release electrons. We've got a range of fancy sectors, which are all those things plugged into the sign that you can see. And they will start reconstructing all the energy, or those X-rays, or the photons that are released by the sample. And they'll reconstruct that into a range of data. So we can look at just the topography of the sample surface. So we can see what shape is happening. If you've got a bumpy sample, that's very useful. But today we're mostly going to be doing backscattered electron imaging and energy disperser spectroscopy. So backscatter, which we call BSC for short, what that's doing is basically creating images based on a density contrast. So it's using the Z number, the atomic number of elements that are present in the sample, to create images on a grayscale, which is what we're seeing here. So in this sort of color scheme, for reference, anything that is white or really light gray is made up of really heavy elements. So in this case, it'll be things like iron. So any sort of heavy element will appear as quite white. Those dark patches are made of elements that are lighter. So if you have things like calcium, which doesn't weigh very much and isn't very dense, you get these nice sort of dark minerals. So it's really useful for geology, because often we have rocks with lots of different minerals in them. They're all made up out of different things. So we can start telling what they are. So this is a really good way for us to kind of like drive around a sample, have a look at things, and get a vague idea of what's going on. From there, we'll take it over into energy disperser spectroscopy, that's EDS. And what that does is our detector can reconstruct all that energy that's being released by the sample and reconstruct it into spectra, into maps, into pictures, which will tell you exactly what element is present, how abundant it is, and where in the sample it is. So we could then combine those two together and get a really good compositional data set for whatever we're looking at. So for rocks, it's really useful. You can learn a lot about a rock based on what it's made from and all the little differences about what it's made from. So yeah, I think that's kind of like the basics. Again, if you do have any questions or want us to explain anything, just let us know. This is going to be pretty casual. We're going to try not to like bombard you with too much in-depth science. We're just going to have fun. So what I'm going to do is I'm going to share the screen that has our software on. There we go, that should pop up. So last night we basically left the SEM running and we got a picture of the whole rock that we've got in there. So it's not a very big rock. It's maybe 1.5 centimeters long. So what this is a backscatter image. So we've got these bright bits here, which are really heavy, and these darker bits, which are made out of lighter elements. These two big white stripes, this is copper tape we're using to hold the sample down in the sample holder, because the last thing we want to do is for it to fall off inside the SEM, because then we have to go in there and get it back, and that takes a very long time. It's very hard. So we make sure everything is stuck down really well and is also really conductive. So copper tape conducts electricity. We've also got a thin layer of carbon over the top of our sample to conduct the electricity as well. And what that does is when the electron beam hits the sample surface and releases that energy, any like spare electrons are being moved away, because the last thing we want is them bouncing around inside the microscope and the detector's picking them up, because then you get really weird artifacts we call charging. These are like big splodges. It can make the image shift and move and distort it, which isn't useful. So we have to make sure that everything we put into an SEM is conductive in some way, shape, or form. So what we're going to do is, if anyone looking at this picture, I'll zoom in a little bit. If there is something in particular you would like us to look at, you can either use the raise hand function, or you can put it in the chat and we will start looking. And if no one has any preferences, we'll just find something fun ourselves.
So before we get started, just to give a little bit of context, so this rock is from a mine in South Africa called Kimberley Mine, which is quite famously known for being quite a big diamond mine. I haven't actually found any diamonds in this, which they are just made up of carbon. So if we find any carbon in there, we might have found a diamond, which might be very exciting.
Keep an eye out for that, because we would like to find some if we can.
That would be cool.
That's our main goal. If we can find diamonds,
that would be cool.
Would be nice. I'll give everyone a few minutes, and as I'll just move around sample a little bit, see if there is anything interesting that you'd like us to start off with. Squiggly lines. It does indeed have some squiggly lines. Left-hand side of the image. Inclusion on the left. Thanks, Dad. Yeah, we'll start looking here. So Lorelei is now going to find this on the microscope, and then we'll be able to start a new beautiful. So it's like Lorelei find it on the microscope. Beautiful. So let that load in on the microscope, and then what our computer does is it will then pull it across into this software. And oh no, that was absolutely the wrong button. It will pull it across here. So this is the same image that we're seeing on the microscope. But through here, we can start doing some little bits of analysis. So all this black stuff around the edge, this is the resin that we have our samples stuck in, because we don't want it falling off anywhere. So already in this picture, we can actually see quite a few different things happening. We've got this big wiggly bit through here, got some chunks of stuff, got some light colored material. So if anyone would like to take over, actually, I'll show you first. First of all, I should teach you how to do EDS. That would be smart, wouldn't it, Jen? So this is a software called Aztec. It's really, really useful. It has a nice little flow chart at the top, which tells you what order to do things in, which I really appreciate. And very straightforward. Once you get onto this Acquire Spectra button, you can basically just start putting little spectrum points anywhere you like. So if we do a test one up there, this is the spectra that it's picking up, and you can see it starts to label different elements that it's found. It also tells us over here the actual numbers of what we're looking at. So I'll put it in weight %. This is basically just how much weight of each element is normalized. So it's a rock. Lots of rocks are pretty much made out of silicate minerals. That means we're always going to see lots of silica and lots of oxygen. Everything else on top of that is kind of the interesting stuff that makes it different minerals. So in this one, we've got lots of magnesium, a little bit of iron, fair bit of aluminium, but not very much calcium, and that little carbon peak at the end is probably just the carbon coat we put on top of it. The EDS itself is very quick, as you can see. So if we do another one here on this big white crystal, we'll see what that comes out. Yep, so remember, white crystals are, or white material is very heavy, so it'll be full of iron. So in this case, we've got iron and titanium and oxygen. I think it's ilmanite. Yeah. So this will be a mineral called ilmanite. So this is a titanium iron oxide. We also find this one in meteorites a lot. It's one of a really, really common iron accessory mineral. If we do say some geology words that you don't understand, please let us know. We're very used to talking to other geologists. So words that we're really familiar with sometimes aren't words that you're familiar with. But this is a pretty typical ilmanite sort of composition. We've got lots of iron, lots of titanium, lots of oxygen, a little bit of manganese. That chromium there, the reason it's put it in red is because it's not really sure that it is there. It could be, but it's not in a big enough quantity for the machine to be confident with. So this is kind of how EDS works. So what we'll do if we zoom in onto a funky little bit somewhere, Lorelei, and we'll let somebody else have a go. Yeah. We'll start a new site. And then we scan our image, we pull it across from the SEM onto our software. So this is just a little bit further into the sample. So not very far from where we were looking. So you've got lots of different shades of gray, lots of different colors, lots of different things happening, which we will try and work out as we go. So if anybody would like to have a go picking some points, let us know, and we're able to give you control of this computer. So you can control all the data collection. Fortunately, we can't give you control of the microscope computer, just in case you drive it into itself and break it, which is sad.
Yeah, also the computer is so old we can't connect it to the
internet. It's also not allowed to be on the internet. So if anybody would like to have a go, use the raise hand function and put it in the chat. We can give you control. And if not, we'll just have some fun doing it ourselves, I guess. Where is Kimberly, my Laura? Okay, that makes sense, I guess. Lots of diamonds in South Africa. Okay. Oh, no one seems to want to take control, so we will acquire some spectra on your behalf. So typically when we're analyzing a rock, we want to get data for every different shade of gray. So we might do one up in this big dark section. And we might compare that to another one just in case it's different. We can do one in like this lighter gray material, and we'll do one in here, which is lightest. So this software is really good because you can just plonk a load of points in and it will just do them all for you. So if you really want to, you could set up 100 points, go away, have a cup of tea, come back, and it'll all be done. So this one is relatively straightforward in composition. So again, we've got lots of oxygen, lots of silica, a little bit of magnesium and iron. Another good thing about this, if I go back to this one, is that we can change the way the different results are reported. So we can either look at the weight % of these things, or we can look at the atomic %. So how many, in this particular spectra, what % is which atom pretty much. And this is really good for working out what type of silicate mineral we're looking at, because a lot of silicates have very similar compositions. So two minerals can have olivine and pyroxene. They're both magnesium, iron, silica, and oxygen. But the difference is that olivine has 4 atoms of oxygen to 1 silica atom, whereas pyroxene has 3 atoms of oxygen to 1 silica. So whilst they look the same in person, and they look basically the same in composition, by using this atomic weight percent, we can work out the difference. So this one is closer to the pyroxene side of things. We can start rounding things up a little bit and call this 60 rather than 58.9 and 20 rather than 18.2. That means we've got 3 oxygens to 1 silica. So this is some sort of pyroxene. So pyroxene is a really common mineral. It makes up basically everything, actually. You can find it in all sorts of lavas. It's a huge part of the Earth's mantle. It's one of the first minerals that forms. And we'll plot back on this, we'll see where we're going. So it's a hugely important one. So we have those 4 points loaded in now. So this last one over here is a little bit interesting. So we've got that titanium back again, but we've also got quite a lot of calcium. So that's something when we see a bit of a weird spectra, a little bit of a weird composition, we might zoom in to and get a better idea of what's happening, especially because it looks like here we've got like some little white patches and some slightly darker patches. So there could be something weird geologically that's going on here. But what we might also do is do a map. Yeah. So like I said before, we can produce pictures using EDS as well. So this is one of my favorite things to do, is we can then go into this map function rather than ID. Now we've got a picture in, we can click start, and what it will do is this electron beam will now scan across the sample all the way across, and it will start basically working out which elements are where, how much of each one it is, and it will create a colorful image. I'm going to flip onto this screen. So this will show you all the different elements that it's mapping and all the different colors that they are, along with the spectra for the whole zone that we're looking at. So often I turn oxygen off because everything has oxygen in it, and it really messes with the color scheme. The hardest challenge in geology is actually finding a color scheme that is nice to look at. Most of them end up looking like 70s bus seat patterns. And it's really hard to get a pretty map out of it. If we turn silica off, that's much worse. That's very bad. But what we can see here is all the different elements that it's finding, and it's all these little individual maps. It's then layering all those colors together to create this. This is a layered image. So what this is going to do, it's going to map the sample a couple of times. So it will go through once. I think it will go through 3 or 4 times in total. And what that'll do is create some really good high resolution data that we can then basically use to start picking out different things. So sometimes there are minerals that look the same. So like lots of heavy minerals will look the same shade of white or the same shade of pale gray. So doing this is really useful to make sure you haven't missed anything. So we can see in here, so what looks like the same sort of white in the backscatter is actually a different thing. It's really yellow, whereas this, which we looked at, and this one, which we looked at, are quite pink. So there's a difference in composition there that we couldn't see just in the grayscale. So that's the benefit of doing maps. And they look nice. If you get a really good one and you print it out big, it's very dramatic. Yeah, and then often we just play around with the color schemes a little bit, try and find a nice one, which is tough normally. But I'm going to give it a go. We'll see what we come up with. Everyone has their own favorite color schemes, I found. Every geologist has certain colors they like being certain things. I always like aluminium to be dark blue. I don't know. No, there's no real reason for it. I do calcium as orange as well. It's not bad. Yep, chromium I always do as hot pink. No reason behind it. I think I just did it once and liked it, so I stuck with it. Iron is always green for me. What color do I do magnesium? I think I do magnesium like blue.
We also always try, so if we're looking at a specific rock and we know that there is a specific mineral that's quite interesting or quite important, so I normally get, I look at mine samples quite a lot, so I'm trying to look at all the metals. So I put iron or titanium or something in a really bright color.
There we go.
Just so that's really obvious when you come to look at it in the map. So it jumps out at you and you know exactly that it's there, and it's a lot easier to see than say if I put it as like a light blue or a yellow.
In the spectacular color scheme that we have going on now, we can start pulling out these big lumps of titanium-rich stuff. And we've now been able to show that it's very different in color to these iron-rich ones. I think this one has one more sweep to go through, and then that's this map made. And the benefit of this is then we can use this map in future because it's storing data for every single pixel. We can then analyze this data again without having to come back on the microscope. We don't need to put the sample back in. We don't need to find exactly what we were looking at again. We can do this all in our own time for fun, basically. So it's pretty good. It makes it much more versatile. I think this one's nearly done. So often we'll do a map, we'll find something weird, we'll go back and look at it. So we might pop back into collecting spectra now that we know there's actually 2 or 3 different sort of dense minerals here. And we might track down and get some spectra for those and see exactly what is happening. So remember, spectra 15 down here was rich in titanium, but also had lots of calcium in it, which is unusual. They're not often elements you find going together. So we might be able to work out what's happening in there. And we've got some extra little things in the chromite map that have popped up that we didn't see before, so we could get a spectra of those and compare them. So it's simple enough. We just pop back into point and ID, back in the same interface, and we can say this bit was full of chromium, and this one was really iron rich, and we can start looking at that spectra now. So this is probably an aluminum chromite. So chromite is another very important mine mineral. We use chrome in lots of things. You often find it with iron. It's got a bit of a variation in its mineral compositions. There are very few minerals that are strictly, these are the elements that go into it. There's always a little bit of leeway. You can always sneak something into the crystal structure. So often we find chromite that is also really rich in aluminium, or it could be rich in magnesium. And this kind of creates a solution where you can swing between different minerals with all kind of the same composition. So you can often go from chromite and go into spinel if you just jiggle things around a little bit, which makes it very interesting. And it also makes the EDS as just a very powerful tool for that. So let the spectra finish off. Yep, so you can see that this couldn't really be anything else other than an iron oxide. It is 73% iron, 25% oxygen, and a few other little things. Yeah.
I'm going to guess that's not right.
Yeah.
Sometimes, it does struggle. So sometimes you get a little bit of an overlap between the, like, so you're looking, Jen points out on the graph, you have these peaks. So they are, each one that's peaked up is unique to each element, but sometimes you can get a little bit of an overlap. They can come very close. So whether it's very low percentage, it might overlap with them, but also because it's such a low percentage, it might also be confused as noise, or it might think that a little bit of noise is an element that isn't actually in there.
In this case, it's using indium and calcium. So the energies that are released when we analyze a sample, they come in different wavelengths. Sometimes the software gets a bit confused. So calcium has an energy of 3.6. Indium has one of 3.2. So it's probably just getting a little bit confused, and it's doing its best. But you do sometimes still need somebody on hand to tell it actually what it's looking at, which is nice. It means we're not completely automated out of a job yet. We're still useful. I think that's all the major things on this particular thing. So we found that this little chunk down here was a little bit weird. There's a bit of a weird composition, a little bit of a weird color happening. So I think we'll do a big zoom in version of that. Because of course these are electron microscopes. That means that we can analyze things up to like 1 million times magnification if you really want to.
Yeah, so
For geology, we often don't go above 400 really.
currently at 850 times magnification, which probably doesn't mean very much without giving you context. So this grain is 72 microns in size.
What's that in millimeters?
That is in millimeters, 0.07 millimeters. So tiny.
Yeah, so it's not very big. It's quite small. But what we can see now is that, yeah, so that weird composition we were seeing where we had titanium calcium together, which is a little bit suspicious. Probably because it's actually got quite a few different things happening. There's lots of different shades of gray in here. So probably this has been a titanium-rich mineral, so like ilmanite, like we saw earlier, that has been altered. So this is a mine sediment, so there's probably some sort of hydrothermal fluids that happened and came through at some point. And what that's done is basically that fluid could interact with the mineral. It can take certain elements away from it and leave others behind, which looks kind of what's happening here. We've got like these patches of different grays, and it's all a little bit messy. If it was like a nice clean crystal, I would be alarmed. What we'll do is, just for good measure, we will do a spectrum there in that shade of gray. We'll do one in this bright white, and we'll do one in this dark. So this middle gray, it's like 18, titanium and oxygen, so it is just titanium oxide.
As a mineral with rutile.
Yeah, so this should be rutile or something along those lines. And again, I'd be surprised if it is actually picking up niobium. Could be, but it's not confident about it. So that's something that we would take to a different machine to double check. But because we're personally not trying to mine niobium out of this, I wouldn't worry about it too much. Again, like this white stuff is titanium cesium, apparently.
Okay.
And it's pretty confident about cesium. Oh no, cerium, my bad. Cerium. These could be. Could be.
I don't know, I've never seen that in.
Yeah. So again, like neither me or Laura actually know this rock very well. So this is kind of how geology works in a lab situation. Get given a rock, you try and work out what's going on. It's got lanthanum in it as well. Yeah. Yeah, and now we've got titanium, calcium, and silica. So this group, this darkest gray through here, is probably an alteration product, is what we call them, where a mineral started to decompose. And that makes sense because it's kind of going around the edges of like these nicer formed titanium oxides, that rutile. You'll also notice how we've kind of got like this nice flat looking mineral over here, like it's a nice sort of, like there's no real texture to it. Or we compare that to this stuff down here. That's because different minerals have different hardnesses. So when we're polishing these flat, which we need to do to get the backscatter and the EDS to work, different minerals fall apart in different ways. So it's the same way that when they're making tarmac for roads, they use a range of rock chippings. They don't just use one type of rock, because that would all just rub down at the same time and ruin a road. Same sort of thing happens here. So we have a range of minerals that behave differently, different hardnesses. Because some rocks are actually really hard to get flat enough to put into an SEM, to do EDS and to do backscatter, just because the minerals keep falling out, which is something to be aware of in sample prep, as sometimes the rock can just fall apart on you. But we're pretty good at not letting that happen these days. Yeah, so potentially a fun little mining deposit. I think it was Spectrum 19 was very strange. So what we've got cerium, that's Ce, calcium, lanthanum.
Yeah,
I'm actually very bad at knowing what elements are.
Yeah, so for reference, we have a periodic table up there. So
We do.
Yeah.
So as all geologists, we work on a very small group of rocks individually. You show us something that isn't one of those, and we've got to start from scratch. And neodymium. So maybe it's a mine sample, so that those rare earth elements could well be in there. In this particular rock, it doesn't look like they're in any great enough quantities for us to have the patience to get them out of there. But interesting nonetheless. But let's go back to the big overview map. That's just the Apatite, the big overview map. So we've been up here in this corner so far. where would we like to go next? You can either ask us directly or you can put it in the chat and we will go there. I'll give everyone a few minutes to decide, or a few moments rather, and otherwise I'll leave it up to Lorelei.
No, no, thank you.
So often what we're looking for when we get a random rock like this is any areas that are lots of different shades of grey, or if there's any like particular big features in there or some weird textures. Elaine Robertson, the right-hand side, and
Anywhere specific?
right-hand side, lower right, inclusion on the lower right. Okay, so we'll aim for down the circular shape in the bottom right. Okay, kind of like theirs. Right, I will set up a new site. Yeah. So what Lorelei is doing now, as you can see on the microscope view, is she's messing around with the contrast and brightness settings, which are notoriously fiddly on this particular machine. Every now and again, it will decide that you're just not allowed to look at your picture anymore because you've gone too contrasty. Yeah, which Lorelei will show you now. Yeah, it actually gets very hard to see things sometimes. Yeah. There you go.
Oh, gone again. Right.
So it's a little bit fiddly sometimes. What we do is we make sure the contrast and brightness is as good as we can on the microscope, because when we pull it across to our Apatite computer over here, it doesn't always get the contrast quite right. There's something in the wiring that just doesn't quite work. But there we go. So let's start this one. So this is that round splodgy bit. And what we can see already is we've got this really weird sort of gritty texture almost.
And then also probably preferentially being polished down when I polish. So I polish the sample. So that blob in the middle is probably somewhere. Yeah. That mineral is probably a lot softer than the stuff around it. So it's just preferentially getting removed as we polish it along to get it to a flat surface.
Although BSC isn't as good as topography, you can still see a little bit of it in there. So kind of like this sort of dark sort of zone here, that's basically shadows from where, again, like Laura said, that we've polished something and whatever grit mineral was in there has just plopped out during that process. Now there's just like a little hollow. But we still got these nice sort of big chunky grey things. This texture in the background is a little bit weird. We can see there are some sort of variations happening. There's a little bit of patches of darker grey. But another benefit of the EDS on Aztec, it does look like a crater. You're quite right.
Yeah, and it is also very pretty to look at.
Oh, you're quite right, Rosie. This is
yeah.
Rocks look really good in SEM. It's one of the reasons that I love doing SEM for geological samples. So because we have all this fine-grained, really sort of fuzzy texture, it's quite hard to pick out individual minerals from that. But what we can do is, rather than just doing a point, a single point, and to get a spectra from, we can just draw a shape. So let's do a circle, and we'll say we want to look at this whole bit, which is all roughly the same shade of grey. And it will now create a spectra for everything inside the area. So kind of like a mini map, but without making a map. And it will give you the spectra for all of it, which is silica, magnesium, iron, aluminium. So probably a pyroxene again, but we'll double check. We'll check the atomic weight, the atomic percent. Oh no, it's a 4. This is an olivine of some sort. Did you get aluminium bearing olivines? Yeah.
I don't know, you know more about olivines than I do.
Yeah. So what we're going to do in post-processing for Microscopy Live is Lorelei and Ash are going to work out the actual mineralogy for this, and we'll make a little pamphlet for everyone so you can see what we've done as a group. What is this white thing? Oh, titanium. So after a while, you get your eye in for it. You can start picking out the really slight differences in color. But you have to look at a rock for a long time or know what's in it to start off with. Yeah, I mean, I would believe the vanadium's in there. That's an acceptable mineral. It might actually be there. Yeah, it's definitely something. So I should specify as well, this little graphy bit, these peaks aren't telling you how much of each element is in there, it's just how strong the signal is. So this is in counts per second, I think. God, it's CPS per electron volt.
Yeah.
Yep, so that's basically just telling you how much of a signal it's getting. It's not telling you how much of the actual element is there. So that's why it recalculates it and we use the weight percent. If we ever want to report data or share it with anyone or talk to other scientists about stuff, we have to make sure that it's in numbers rather than wiggles. Unfortunately, the wiggles are nice to look at, but they're not particularly useful in terms of science. So it's qualitative rather than quantitative, which I always struggle to say. That's okay. Could we do a zoom in on some of this fuzzy texture and get an idea of what's there? Yeah. So we're going to zoom in. I think we're kind of like in this area. Yeah, that'll do. I'll do nicely. And what we'll do is we will. Oh, you're fine. Yeah, it's weird, isn't it? I can put the contrast up a little bit. Oh, that's a smidge better. Yeah. Yeah. So this scale bar at the bottom is 100 microns. You can see like all these individual little crystals are quite small. Zoom all the way in I can on this map, which is just a digital zoom. It's not actually microscope. Like lots of these things are still smaller than 10 micron, which is tiny for geology. There are some material scientists that we work with here, Tom and Dan, who'd be horrified to hear me say that 10 microns is tiny. But it is. It's very small for a rock. So I'm going to put it back into apply a spectrum mode. I'm pretty sure you all know how to do EDS by now. We've got our little buttons here. You just draw shapes, you point some points down. So if anyone feels particularly brave, feel free to request control and we can let you have fun with it, really. Draw some shapes, get the spectra, and we'll try and work out what it is as we go. Oh, something else. That's okay. So what we've got this kind of like middling grey, we've got a couple of lighter grey bits, we've got this dark grey thing up here. So what I'm going to do is do a fun little freehand region, which will be tough because I'm not very good at drawing with a mouse. So what we're going to do is draw around the middle of that darker grey blob. And it will now make a spectra for the whole middle bit. If we slide that up so we can see the whole thing. Silica, magnesium, aluminium, iron. So kind of the same elements that we're seeing everywhere, which is good. We like a rock to be consistent. A little bit of calcium, that's fine. It's a weird little rock. It can have some calcium in it as a treat. And I'll line up a couple of things. We'll check this white blob, and we'll check that white blob, and we'll see what's in there. Just iron. Always a big fan of minerals that are just one thing. You can't really get it wrong.
Makes it a lot easier to deal with.
Nice and straightforward.
Yeah.
Yeah, a little bit of magnesium, that's fine. That's fine. So I should also say that when we do EDS, we're quite careful about where we put our points down. So I say we can just plonk them down anywhere, which you can. But if you're trying to work out what a specific mineral is. And if it's quite small in particular, you have to be really careful about where you put your mouse down and where you click. So that's because as we send this electron beam down into the sample and it excites those atoms at the sample surface, it's actually exciting kind of like a little blob around it as well. So although the beam might just be going down in one place, you're also getting data for a little bit of area around it and slightly further into the sample as well. So the higher power beam we have, if we rack this up to 25 or whatever it goes up to, 20, okay, that's fine. Yeah, so if we increase that, that would make that interaction volume, that little blob we're analyzing, bigger. So if you're looking at really small things, you tend to narrow down and reduce the voltage to minimize that. For this kind of rock where everything is just really fuzzy, I don't think it would help very much. But it is an option that we have. So although we can be pretty gung-ho about it today, if we were doing some actual analysis for, say, an actual mining company, they had like some little crystals they wanted us to check, we'd have to be very careful about what we do. That's kind of this area. It's this weird fuzzy texture, isn't it? I think like these darker patches through here, this is probably the result of either oxidation, or it could be some hydrothermal stuff. But if we go back to the overmap, where are we? Montage data. And so we've done this bit up here. We've looked down here. Where else would we like? So this big gray chunk looks like it's got a fair bit happening in it anyway. This is also lots of different minerals and lots of different things. A couple of light spots every now and again. So let you decide where you want to go next. And as always, if not, it's entirely up to Lorelei because she's driving the microscope today. What's going in the top right? Looks like the light grey bit is cutting through the darker bits. I would say you are completely right. This bit up here. Yes. Laura is just going to drive all the way across. Make a new site. We'll just let everything in focus. Beautiful. Finish pulling across. Well, that looks like a lot of things happening.
Yeah.
This is a very busy little area. So the bit that I think Nat was referring to is this bit through here. So what we've got is these two darker grey things, if you think of the same crystal, or the same mineral at least. They might not be the same crystal, it doesn't look like they joined up properly. Yeah, some sort of mineral fragment and infill situation. It could well be dislocation, Nat, you are quite right. So I think this would be a good one to actually start off with a mineral map. So we can work out all the different things that are happening. So again, we put it into the map function. We go to acquire map data first, and we hit start. And lo and behold, it starts doing things. So I personally always like to watch it in this construct maps thing so I can control the elements that are showing up and the colors that they're in. Which I'm going to go through now. We're going to put it back into our favorite colors. So I always have aluminium as dark blue because it makes the project place stand out really nicely. Orange for calcium. Green for iron. We'll turn iron on so we can see it. Titanium is red normally because it shows up really nicely. Got big chunks of titanium already. Let's see what comes through. So it looks like we've definitely got some bits of titanium. We've got some bits of iron oxide. This lighter material going through here is much richer in calcium. So you can see it in the calcium map down here. You've got like this dark patch where there's not very much calcium and this big brighter chunk through here where there's much more of it. There's probably some sort of hydrothermal thing would be my first bet. Let's see what else.
So when we say hydrothermal, I think that's the best way to describe this. So,
Hot water.
yeah, basically, obviously there's water underground and that flows. In some areas, the water can get really hot and it will flow through the rock, and sometimes it will cause a lot of alteration or destroy things, or it will cause deposition of minerals that are in the water. My mask keeps slipping, right? Definitely looks like hydrothermal stuff.
No worries, that. Yeah, so if you basically dunk a rock in some hot water for long enough, like geologically long enough, it will start basically sort of soaking up elements from different minerals as they break down. So if you've ever been to Iceland, all the hot water there smells like sulfur because it is full. It's full of sulfur. It's basically sucked up all that from the rocks. It's also why water tastes different in different places. So the water in Bath tastes very different to the water in Scotland, and that's because the types of rock that water in the aquifer is sucked in. So in Bath, it's limestone mostly, so it's really hard water, and that's why your kettles end up full of limescale. It's all that calcium that's falling out of the water as you boil it and precipitating onto your kettle.
So in areas of Bath, the southeast,
yeah,
very hard water. This is where this like hard water, soft water comes from. So in the southwest here, it's all
not too bad.
It's not too bad. We've got quite soft water here because obviously the water goes through rocks that it can't gain any minerals in. So yeah, basically.
As you travel around, you'll find that the water does taste different in different places. I remember the water in Berlin being absolutely disgusting. It almost tasted sweet, and that's just because the type of aquifer that Berlin sits on. So an aquifer is an underground sort of porous rock where all the water sits, and that's where we get our groundwater from. That's where it all goes. That's where it all comes from for us as well. So we've got a new mineral popping up here. We've got this really bright calcium spot there, which is this one. Apatite, maybe? So we'll definitely give that a zap. Lots of potassium in here as well. It's nice. So now we've got this map, which is just finishing off. We can use this to kind of pick up the different minerals we want to look at and get some spectra for. So we'll definitely do this weird sort of high calcium orange spot. Got some nice titanium bits. This could be quite nice. We've got titanium and iron together. Yeah, but this is a good way to see actually that this lighter grey stuff in the middle is very definitely different composition to that darker grey, which is now the sort of dark green colour. So there's that enrichment in calcium, which is quite a light element that is making this appear lighter in the grayscale. Remember, the backscatter works by density contrast. So lightweight elements are lighter, dark in colour even, and high density elements, so all that white stuff, show up very differently. So if we go back into point ID and we acquire some spectra, it will now show us that layered element map, which is nice. It makes it easier to find things. We want to look at this one. If I show the whole thing. Oh, so this is calcium, oxygen, and phosphorus.
Yeah.
In my head, P should stand for potassium, and I always get it confused. And I've got a PhD and should know better. Yeah. 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 So this is a mineral called apatite. So it's quite a pretty mineral actually. It's normally sort of like, I think it ranges between green and pink depending on what's in it. But there's a couple of different versions of apatite. We can have fluoroapatite, which is this one. So it's got fluorine in its crystal structure as well. Or you can have fluoroapatite, which has fluorides, which is less common. Most apatite will be fluoroapatite. It's quite a pretty mineral. If you ever get the chance to see some in person, would highly recommend. It's quite nice. We've got this big titanium splodge up here.
Yeah, and also a fun little fact for you: apatite is basically the same mineral that your teeth are made from. The fluorine version, which is why everything needs fluoride in it, and fluoride because that's what your teeth are made up of.
Yep, that is good for you. Probably shouldn't be chomping down on apatite though. It's
No.
digestively probably not the best thing for you to do.
Yeah. And it'll probably cause it to more harm than good.
Yeah. Yep. So what we could see was titanium rich on the map is definitely titanium. It is rutile again by the looks of it. So we've got this iron rich one down here. Yep, so there's an iron oxide with a little bit of titanium in it, which isn't a surprise because it's got that big band of titanium around the edge of it. So there's probably a little bit in the middle too. And I've also found, which when this one finishes, so the next spectral pop-up is this little sort of blue splodge here, which I didn't notice before, but it's a definitely different color to everything else that we're looking at. And for good measure, I'll put one in here as well, and one in there, just so we're covering all our bases. So again, we've got that aluminum chromite happening. So it's chromite, iron, aluminium, and a bit of magnesium and titanium, which is a pretty standard composition for these sorts of things. Like I said earlier, you can fit a lot of different elements into a crystal structure if you try hard. We'll let these ones finish off, and maybe we'll just do a final backscatter image of one of these little intergrowths, and then that will be the end. So we're very nearly done. We'll just get these last two spectra, and we'll just do a quick zoom in on something else. And we'll leave you with a pretty image to finish on. Not whatever horrid color scheme I've made here. I've made worse. I've definitely made worse.
Yellow is the main color.
Yeah.
It doesn't. It's faded pale green, yellow.
Yeah.
Not pretty to look at.
Yeah, so silica, calcium, magnesium, iron. That's this lighter stuff through here. So let's check the silica to oxygen ratio. 3. That's could be pyroxene, some sort. Pretty high calcium. Probably lots of different things, I would imagine.
If you do have any questions, just pop them in the chat or
pop them in the chat. We're happy to hang on. Yeah, we're happy to hang on a few minutes afterwards to answer questions if you'd like.
Also, if you aren't comfortable asking us any questions on here,
also
that's
fine.
If you went back into the booking form, you'll find both of our email addresses and my phone number. So if you want to ask us any questions afterhand, we'll more than happy to answer them for you.
Zoom in on this little interest, and we'll finish on a funky little.
Fluffy.
Yeah.
Very fluffy.
We'll pull this one across. So I've just zoomed in a little bit. Again, you can see how all the stuff in the background is really, really fine grained. Lots of little crystals rather than one big crystal. Actually, could we zoom in again? Yeah, get some fun intergrowth patterns happening. That's quite a lot for Jonathan.
That is quite a lot. Cool. Look at all those funky textures. Yeah.
Cool.
Lots of cubes.
Zooming in all the way again, and we'll leave you with this one. So we've got like these nice sort of cube minerals and these nice sort of like well-formed crystal shapes. We call these euhedral, which just means they're formed really nicely. They're about as perfect as you can get. But we'll leave you on this little splodge of titanium up here. Because if we zoom in a little bit, you can see kind of like this sort of fuzzy intergrowth through here. These are tiny little iron crystals that are starting to grow, and unfortunately just didn't quite make it into anything big before it got dug out the ground. But we'll probably leave it there, I think, for today, because 3 minutes to 12, nailed it pretty much perfectly on time from our side of things. If you do have any last minute questions, let us know. And yeah, I hope you enjoyed it. So next time, I think we're going to do microfossils.
Microfossils or microplankton from
Microplankton, yeah.
In the sea. So all of those little tiny creatures and shells that are not really visible to the naked eye.
Yeah.
It was highly requested. Will this recording be made available online?
Yeah.
Yeah.
So what we're going to do is we are, once we've got the recording finished and we've got it sorted up, we are going to basically send it around to everyone who registered, because some people who registered weren't able to make it today. So you'll get a copy of the recording, and we'll cut out our favorite bits probably for somewhere, and then we can put them up on YouTube as well. The next one is the last Friday of November. 26th of November.
I haven't quite finished making the website and all the booking forms, but I will do that next week and I will put it online.
Yep. So we're doing Microscopy Live last Friday of every month, apart from December, which will be the second to last Friday, because we want to go home for Christmas.
Yeah, it's the 24th. Yeah,
Yep.
I'd rather be home.
Yeah. Yeah, so hopefully we'll see some of you at the next one. If you do have any ideas for future events, let us know. Drop us an email. Find us on Twitter. However you can get hold of us, feel free. If there's anything particular that you would like to have a look at, we've got some ideas already, but we'd like to know what you, the public, like to see. And we can play with some of the other microscopes that we have in here as well. Let's hang on for the last few questions. Oh, thank you, Rosie. That's very kind of you. Did you have some?
I did.
Good. Good. So keep an eye out for your emails. We'll have a video and a little pamphlet for you. So hopefully we'll explain some bits about what we found once we've narrowed it down a little bit, because we'll need to do some maths to work out exactly what minerals are happening. Do a little bit of reading. Cool. Yep, if you have any questions in the last few minutes, just let us know. And if not, we will hopefully see you at the next one. So have a good day, everyone. Thank you so much for coming. We had a great time. In future, we'll have other members of the team helping us out. So individual specialists for different fields will be joining in, so it won't always just be us two. You'll get to meet everyone else who works here at the Plymouth Electron Microscopy Centre too. Oh, yeah, interesting this. Stop sharing this one now, if I can. I'm so bad at Zoom. Oh yeah, there we go. There we go. Yeah. Cool. We'll see you at the next one, guys. Thank you very much for coming.